so for this final video on simple harmonic motion, okay, we're going to look at damping. Okay, so for all the previous ones, we've always ended with our x double dot equals minus omega squared, minus omega squared x. Okay, that's when we've got simple harmonic motion full stop. Okay, now, however, we can have scenarios in which it does like a bit of simple harmonic motion. Okay, now the key one that we got to look at is the fact of for damping. Okay, and this is when we use, for example, Newton's second law, we end up with a solution that looks like this. Okay, where we've got x double dots plus kx dots plus omega squared x equals 0. So we still have our components. We still have the omega squared x. We still have x double dot. We also have some sort of component of velocity in our equation. Okay, now from there, we've got 3 different types of damping. Okay, and it all depends on how our auxiliary equation is going to work. Okay, so if I use my auxiliary equation, that's doing like my whole let x equal e to the mt, and then differentiate 1, differentiate twice, sub it in. Okay, ends with this, and then we use quadratic formula or whatever method for solving. Okay, we've got 3 situations when we solve this kind of thing. Okay, we either get 2 distinct roots, we get equal roots, or we get no real roots or complex roots that you now know about. Okay, so each scenario means a different kind of damping. Okay, so for the first one is 2 complex roots. Okay, and this is going to give you your general solution of this. So this is where we're going to link some of our pure work in. Okay, this is light damping. Okay, so if I get complex roots, I get light damping. Okay, and I can use this general solution here. Okay, now if I get 2 equal roots, then I've got critical damping. And I can use this general formula again from the pure stuff. And the other one is if you get 2 distinct roots, okay, then we've got heavy damping. Okay, now the key kind of like difference between these is like how quickly the simple harmonic motion ends. Your light damping, we kind of get the scenario of it does like little by little, just does less and less of a turn of my simple harmonic motion. Critical damping means it kind of plateaus off fairly quickly. So if it starts at the top, for example, it may do like 1 and then stop. Okay, whereas heavy damping would literally barely complete 1. Okay, so those are like our 3 situations of when they happen. Okay, so the key bits are still going to stay the same, and that's going to be, okay, what's my equilibrium position? Okay, then let's apply Newton's second law, and we're going to end up with a second order derivative like the one at the top. Okay, and then we're going to find its general solution like we normally would. Okay, and then sometimes we get asked what kind of damping it is. Okay, and at that point we have to realize which one it is. So we've seen this question before. Okay, but it's really, really good question because it kind of like applies everything that we need to be able to do. Okay, so the first part A. Okay, I've got a particle of mass 2 kilograms is attached to a spring of modulus 8.4 of natural length 0.35. Find the length of the spring whereas when the mass hangs in equilibrium. Give your answer as a fraction. So it's an equilibrium. So again, if I draw my general kind of thing hanging down, I've got 2g going down, I've got tension going up. Now if I put my lengths on as well, I know this is 0.35. I don't know what the extension is. I want the length, so I want the overall length here. Okay, so I'm going to find the extension and I'm going to add it on. So let's do equilibrium. Very similar to the previous example that we did. It's going to be tension equals 2g, and I'm going to apply everything in. Okay, so I've got lambda, which is 8.4, times x, which I don't know, all over 0.35, and I'm simply going to solve that for x. Gives me 49/60. Now that's the extension. It wanted the length of the spring, so I want the full length. So my length is going to equal the 49/60 plus its original length of 0.35, which gives me 7/6 meters. Okay, so that's where its equilibrium position is going to be. Now, this is where we need to be careful. The spring of the particle is placed in a cylinder full of oil, okay? With one end of the string attached to the top of the cylinder. The height of the cylinder is 1.8 meters. The particle is released from rest at the base of the cylinder as shown in the diagram. So it's going to be released from rest down here. It's going to bounce slowly backwards up. The displacement of the particle from the center to the top of the cylinder at T is x. As the particle moves, it experiences a resistance force of magnitude 14v, where v is the speed. Show that, and then this is my second derivative. Okay, so remember x double dot and x there, and x dot there. So let's get a diagram drawn. I'm going to have, it's pulled all the way to the bottom. It's still going to have 2G pulling it down. It's still going to have tension pulling it up. Okay. It's also going to have its resistive force moving up, which I know, I'm going to have a little arrow going up, is 14V, so 14x dot. Then, because the equilibrium position is somewhere up here, okay, I'm going to have to think about the fact that my extension, so my length here, let's call this length from the top x, that's what it says from here, from the top of the cylinder, is x. So that's x, which means x dot must be going down, x double dot must be going down. Okay, so that's going to help me with all my forces and stuff in a moment. Okay, so first of all, let's do our normal thing, Newton's second law downwards. So down I've got 2G, up I've got the tension, and up I've got the 14x dot. And that's going to equal 2x double dot. And now let's do the same thing we normally do. So 19.6 minus t is going to be 8.4 times its extension, which is going to have to be this orange length, which would be x minus the original length, which is 0.35. All over 0.35 minus 14 x dot is 2x double dot. Okay, and then from here, we're just going to slowly rearrange and solve this equation. Okay, now in this scenario, let's think, I want it to look like this. So I'm going to kind of like tidy up this fraction bit first. So I end up with 19.6, and then I'm going to divide by 0.35 and expand my bracket at once. I'm going to get 24x plus 8.4 minus 14x dot is 2x double dot. Now I've got to think about, I want everything on one side. Keep your x double dots positive because it is on this side. Okay, and I'm going to end up with 28 is 2x double dot minus 14x dot positive 24x. And again, I want it so it's, look, we've got 14 here, so let's divide everything by 2. Gives me 14 is x double dot plus 7x dot plus 12x. Okay, and there it is. There's my equation as they required it. Okay, now you could technically change them back to d2x by dx squared and dx by dt. That's completely fine. But leaving it like that would be completely fine. So part B, so part 2 is going to be finding my general solution. Okay, so I've currently got x double dot plus 7x dot plus 12x is 14. Okay, now it's because it doesn't equal 0, that means I need to do my CF and my PI separately. So let's do my CF bit first. Okay, so I got my x double dot plus 7x dot plus 12x equals 0. Now if I do my whole let x equal e to the mt, then I'm going to have m squared plus 7m plus 12 is 0. And I can just factorize and solve it from here. Okay, so I'm going to get m plus 4 and m plus 3 is going to be my two numbers. So m is minus 4 and m is minus 3. Now, before I actually go on, although part 3 wants to know what type of dampener it is, at this point here, I should be able to tell what kind of dampener it is depending on the solutions I've got. Okay, now I've got 2 distinct solutions, means it must be heavy damping before I go any further. Okay, So let's keep going. That means that for my CF bit is going to be a e to the minus 3t plus b e to the minus 4t. Okay, and then from there, I also need to do my pi. So I'm going to go up to here and do my pi. So now you think about what I'm going to let x equal. In this scenario, I'm going to let x just equal lambda because it's only a constant on this side. So x dot would be 0 and x double dot would be 0. So I plug it into my quadratic, so my second order up here. I've got 0 plus 12 lambda is 14. So lambda would be 7 over 6. Okay, which is kind of just a coincidence. That's our extension for its equilibrium. Okay, which means x would equal 7 over 6. So therefore, general solution is going to be x equals 7 over 6 plus a e to the minus 3t plus b e to the minus 4t. Okay, now lots of people would naturally stop there. Okay, however, I need to find a and b. Okay, so now I need to keep going. I need to try and find it. So you think of some things they told me. Well, they told me basically it was pulled down to 1.8 and then released. Okay, so it's pulled all the way down to here. So I know when time is 0, its velocity is 0, and it's down at the bottom, so its x is 1.8. Okay, so that's what I'm going to use to try and solve that. And I'm going to go to the side over here, okay? So I know that when t is 0, x is 1.8 and x dot is 0. Okay, because velocity is 0. So I can plug in the first ones into this general equation here. So I end up with 1.8 equals 7 over 6 plus a plus b. Okay, which I can rearrange, okay, to give me 19 over 30 is a plus b, and there's one equation. Okay, now I'm going to do a very similar thing for the next thing, but I need to do x dot. So first of all, let's find x dot. Let's differentiate this line. I end up with minus 3a e to the minus 3t per minus 4b e to the minus 4t. Okay, and then we're going to sub in my values again. So I get x, now I've got 0 equals minus 3a minus 4b. And there's a second equation. Okay, now I'm simply going to solve those two simultaneously. And I end up with a is 38 over 14, and I end up with b is minus 19 over 10. Okay, so therefore, x equals, and let's plug them in, 7 over 6 plus 38 over 14 e to the minus 3t minus 19 over 10 e to the minus 4t. Okay, so there's my general solution. There's x in terms of time. And the final question wants to know what kind of damping it is. And we already said it up here when I got two distinct roots. It must be heavy damping. Okay, most of that work at this bottom section down here was all your pure stuff. Okay, the only difference is getting this first equation. Okay, so I wouldn't be surprised if they did throw something like this in, that your first part wasn't to show that. Okay, and then if your second parts were, then okay, find me a general solution. Okay, quite a difficult question. Okay, quite a lot for us to do, but definitely manageable. So let's remember again your key points up here, which have disappeared for me. Okay, fine. Is the light damping your critical damping and your heavy damping? So light damping means you've got two complex roots. Your critical damping is when you've got equal roots, and then your heavy damping is when you get two distinct roots. Okay, but apart from that, okay, that's the end of simple harmonic motion and the end of Unit 6. Okay, so thank you.